best to write x as a sum of indicators, where each indicator has two values, 1 or 0, with probability p and 1 minus p respectively. And by properties of expectation, the expectation of an indicator is just the probability that that indicator is 1, namely p. And furthermore, then if all the indicators have the same expectation, then the expectation of the random variable will just be n times p. This was the case when x was binomial, since binomial is a sum of independent Bernoulli trials, Bernoulli p trials. It was also the case when x is hypergeometric, which is a sum of dependent Bernoulli g over n trials. So in both cases, we disproved formulas for the expectation of binomial and hypergeometric. Today, we're going to review student concept test responses. We'll look at another example of expectation with indicators. We'll look at a tail sum formula for expectation, and we'll also look at Markov's inequality. So last time, a forgetful valet is attempting to return n cars to their n rightful owners. For each driver, the valet remembers the car correctly 5% of the time. Otherwise, the valet retrieves a car at random, possibly the correct car. What's the probability that the second driver retrieves his own car? Well, the answer was B. One person says everybody should have the same probability. This should be symmetric across the board. Another student says, I think it's n instead of n minus 1, since it's like drawing from a deck where the probability of the second card being a specific card is the same as the first. One person writes, there are two options. The valet remembers the car, and the valet randomly retrieves a car. For this 95%, there's n minus 1 cars left because the first driver already drove away a car. So this is wrong because these probabilities are unconditional. So the valet for the second driver does not depend on what the valet does for the first driver. You can think that the valet does not take the car. There are still n cars there for the second driver. Another person says, considering the limiting case n is 2, the probability that he gets his car should be slightly more than 50%, which is given by B. So I like that he's thinking about limiting cases. So notice that in case C, if n is 2, that would give you 1. And so the probability that the second driver retrieves his own car is not 1, because we're not assuming that the valet gave the first car to the first driver. So now the second part of that concept question just asked you to calculate the expectation of n, which is just n small n times the probability that you computed in part 1. So here's another expectation question. Consider a 5-card deck consisting of 2, 2, 3, 4, 5. Let x be the number of cards before the first 2. What's the range of values of x? Well, it's 0, 1, 2, or 3 because there are between 0 and 3 non-2 cards before the first 2. Write x as a sum of indicators. So here, instead of the usual I1, I2, I3, I'll write I3, I4, I5, where 3 refers to 3, card 3, the card that is 3, 4, and 5. So these are the non-2 cards. And notice that this x will take values between 0 and 3, so that looks right. I'm going to define, for example, I4 to be 1 if 4 is before the first 2 and 0 otherwise. The chance of that is a third. You can just think calculating the expectation of I4 only involves 3 cards, 4 and both of the 2s. And that 4 is either before the first 2, between the two 2s, or after the first or after the last 2. So so it's 1/3. All of those options are equally likely. Find the expectation of x, so that would be 3 times a third, or 1. So then we did a concept test. Consider a well-shuffled deck. The expected number of cards before the first ace is, so it's 48 over 5. Essentially, you have 48 non-aces, and we have 4 aces, hence we have 5 slots, as shown in the picture here. You can just think that basically to find, let's say, the second the expectation of the second indicator, which would be 1 if the second non-ace comes before the first ace. There's only 5 relevant cards here. You can throw away all the other cards in the deck. So we have 4 aces in this non-ace, and there are 5 equally likely options. That non-ace can come before the first ace, between the first 2 aces, and so on. You have 5 options, which I've represented by the 5 slots in this picture. So the probability is 1/5, and the expectation then is 48 times 1/5. The second part of the question was just the expected number of cards between the first and the second ace. And there's nothing special about the second and third, the first and second ace. So the answer will be just the same as it was for the first question. We then did a tail sum formula for expectation. This is useful in certain situations where x is the maximum of a number of random variables. So to derive this, say that x is a count. It needs to be a count. By definition, x is 0 times the probability that x is 0, plus 1 times the probability that x is 1, plus 2 times the probability that x is 2. Let's write that as 1 times p1 plus 2 times p2 plus 3 times p3, and so on. You can write this out, all these probabilities, and you'll see that now the columns are precisely probability that x is greater than or equal to 1, probability that x is greater than or equal to 2, and so on. So then the expectation is the sum of all of these tail probabilities. That's called the tail sum formula. So this is particularly useful when sometimes it's easier to find these tail probabilities than it is to find the probability that x is any particular value. So as an example, a fair die is rolled 10 times. Let x be the max of x1 to x10. Find the probability that x is greater than or equal to k. Well, the probability that x is greater than or equal to k is 1 minus the probability that x is less than k. And if the max is less than k, then all of the, if x, the max, is less than k, so that means that all of your x1, x2, up to the max, then clearly all of these xi's are less than k. So then we have independence, so it factors, and you just get 1 minus probability that x1 is less than k to the 10th power, and you can write a formula for that. So then the expectation of x, you can just find all these probabilities and work that out. So here's an example. If a fair die is rolled 3 times x1, x2, x3, let y be the sum of the largest 2 numbers. So notice that you can write y as x1 plus x2 plus x3 minus the minimum okay, and we're asked to find the expectation of y eventually, and that's what I'm going to ask you. So you could break this up. You can see that you can break this up because the expectation of y will be the expectation of x1 plus expectation of x2 plus expectation of x3 minus the expectation of the minimum. And to find the expectation of the minimum, we're going to use tail sums. And so, for example, the probability that the minimum of x1, x2, x3 is greater than or equal to 2, you can calculate that and show that that's 5/6 to the third power. And so then the expectation of the minimum is going to be the probability that the minimum is greater than or equal to 1 plus probability that minimum is greater than or equal to 2, and so on. And you can show then that this is the boxed formula there in blue. And then, so the expectation of y will be, so you're going to need to find the expectation of x1. And so just use the definition of expectation in that case, since it's so simple. And so basically the expected outcome of rolling a die is 7/2. So that's not that surprising. It's 3.5. So then the expectation of y will be 3 times that plus the result that you got above. Finally, Markov's inequality. So this gives you an upper bound for the probability of being in the tails. So you require that x be a non-negative random variable and a being a positive number. The expectation of x is the center of your distribution, right? And probability that x is greater than or equal to a is the tail, the probability of being in the tail. The box formula is the Markov inequality, and I show here an example. So let x be the yearly outcome of Bay Area residents. The expectation of x, let's say, is 100,000. Find an upper bound for the probability that x is greater than or equal to 500,000. So the answer to that would be, by Markov's inequality, 100 over 500, or 1/5. Another example I did, x1 to x100 are independent, identically distributed Poisson 1/100s. S is the sum of those. Now we remember that the sum of those is Poisson 1, right? So I asked you to draw that histogram and find the probability, approximate the probability that S is greater than or equal to 3 using Markov's inequality. So S is Poisson 1. We know the expectation of Poisson 1 is 1, and I can just make that histogram. And so by Markov's inequality, it's less than or equal to 1/3. That's 1/3. Yes, 1 is the expectation and 3 is a. You could compare that with the true value and see indeed that it is an upper bound. It's not a very good one though. Finally, a proof of Markov's inequality. Very simple but beautiful. Let's note that expectations have the property that if x is less than or equal to y, then the expectation of x is less than or equal to the expectation of y. And to prove Markov's inequality, we're going to look at this indicator that x is greater than or equal to a. So in other words, it's 1 if x is greater than or equal to a. So a times that indicator has two values, a and 0, and it's a if x is greater than or equal to a. So we're going to compare two random variables, a times that indicator that x is greater than or equal to a, which I've drawn for you in gray here, and the diagonal, which is y is equal to x. So notice that a times the indicator is always less than or equal to the diagonal y is x, because it's always underneath the diagonal. And so applying expectation to both sides and dividing by a gives you exactly Markov's inequality. Have a great weekend. I'll see you next time.